Welcome to the June 2025 MIDAS webinar. It's my pleasure to introduce Dr. Wasiur KhudaBukhsh this afternoon. Dr. KhudaBukhsh is an assistant professor in the School of Mathematical Sciences at the University of Nottingham in the UK. So we appreciate you being on what must be close to hopefully the end of your day or getting close to that. Dr. KhudaBukhsh is primarily interested in probability theory and statistics and their applications to epidemiology and systems biology, particularly in terms of studying epidemics on random graphs and developing methodologies for parameter inference. And I think that's what he's going to talk to us about today. So without further ado, Dr. KhudaBukhsh, the floor is yours. We're looking forward to hearing your talk.
Thank you very much. It's wonderful to be giving a talk at the MIDAS webinar. It's a great honor for me and definitely a great opportunity to share some of the things that I've been developing over the last few years. So I work on epidemic models on random graphs and also mass action networks, which are complete graph setup. But I thought today I'll talk about a statistical problem, which is the problem of parameter inference when we don't have enough data. We don't have, in fact, I'll be working in a regime which I call the extremely sparse regime. It's a made-up term that at this point only I use, and I haven't heard anybody else using it, but I'll explain why I call it the extreme sparse regime and what it is. So to basically just motivate the problem, so here's what I'm going to talk about today. It's basically if we have an epidemic model and we want to estimate its parameters or quantities of interest that are functions of its parameters, for instance, the basic reproduction number, how do we estimate the parameters of an epidemic model when we do not have any population level data, which is typically the case because we don't know the size of the susceptible population. We don't even know the prevalence because there could be underreporting and various sorts of issues with it. And instead, what we have is a small sample of individual level data, so which are possibly censored or even truncated infection times or recovery times or hospitalization times or even death times, which may be noisy. So the basic premise is, how do we estimate parameters of a population model when you have a small sample of individual level data? So the method that I'm going to present is called dynamic survival analysis. And it's a method that that we developed as joint work with Gregory Impala, Eben Gana, Bosung Choi, and recently with Arnab Ganguly. So a lot of different people contributed to developing this methodology. To make things a bit more precise, so let's consider a pure death type dynamical system. I will be denoting them as, so this is simply a system that goes from S to the empty set, which is simply just as to say that you have some susceptible individuals who die at a particular rate, and it's a population level model which could be described by an ordinary differential equation that looks like this. So you have ds and dt, which is just minus h of t and s. So it could also depend on time. Now, if this type of system, of course, then of course this looks like a decreasing curve. I will be assuming that that h is positive and Lipschitz continuous. And the question that I'm asking is, how do we learn a population model like this? Well, if we are able to observe, let's say, some population counts at different time points, then you can think of fitting a least squares method or some other method that you can think of. But if you are in a situation where we want to learn the parameters of this system, which I'm denoting by theta here in this model, then how do we learn the parameters when we have access to only a random sample of death times of some individuals observed up to some time tk. So a typical situation that we should have in mind is if we have only infection times of some individuals in a large population, but we don't have incidence, we don't have a prevalence, and we don't certainly know the size of the susceptible population. And this data could even be truncated or noisy or censored, or both interval censored. So for instance, a typical data could be that you know that some individual got infected at time 10.3 and 0.1, or during some interval 0 to 2.5, and so on and so forth. So this is what I call the extreme sparse regime, because from this type of data, you actually cannot construct the system state. You're getting individual level data, and it gives you some information about the population, but you cannot construct this. So this is the system. Now, the main message of this talk is the following, which I want all of you to remember, and maybe if there is only one takeaway in this whole talk, it is basically this. So if my system is, as I described, is ddt of st equal to minus ht, then an asymptotically exact likelihood function is based on this type of data is simply the product of the negative derivative evaluated at those time points, normalized by, if capital T is my the final time window, 1 minus s of t to the power k. This is going to be an asymptotically exact likelihood function. It may appear as ad hoc, or it should rather appear as an ad hoc quantity to look at, or to be trying to maximize if we want to estimate parameters. But I will explain why this is not so ad hoc, and there is rigorous theory to justify it. So once we write down this likelihood function, then we can simply maximize it to get maximum likelihood estimator, or we could multiply a prior and then go Bayesian and do Bayesian inference. So this type of likelihood function is called the dynamic survival analysis likelihood function, and it has been, so we developed this method while we were working as part of the COVID-19 response modeling team at Ohio State University, supporting the governor of Ohio and Ohio Hospital Association and Ohio Department of Health. So it's been more or less 3 years that we've been looking at systems like this, and yeah, okay. So let's look at maybe some examples. So questions to mathematical biologists. You might be wondering, okay, it seems like a very simplistic system, just a pure death type of systems. So what other systems are reducible to this system or can be represented by this type of system? So the first example is the standard mass action SIR model, Markovian model, the deterministic case, which boils down to a system of ordinary differential equation. This is a special case of Kermit-McKendrick's paper on integral equations, renewal equations rather, so which was published in 1927, so almost 100 years ago. Here beta is supposed to be the infection rate, and gamma is the recovery rate. And you get this system of equation, and we assume certain initial conditions that S0 is equal to 1 and I0 is equal to rho, so some positive parameter. Then using fairly simple algebraic manipulations, you can show that this system can be reduced to a single equation, which is given at the bottom here. So the right-hand side of this time derivative is precisely the function h theta in my case, and theta will be beta, gamma, and rho. So if I observe a random sample of infection times, T1, T2, Tk of k individuals, then the likelihood will look like just the product of the negative derivative of s, which is simply beta times s times I, evaluated at those time points, normalized by 1 minus s capital T, if our observations are from 0 to capital T. Okay, so this is one example. The other example is an SIR model on a configuration model random graph. We all know that mass action models are not necessarily very realistic, because mass action models typically assume if you are infected, you are able to infect any susceptible individual in the population. So with certain probability, which is positive, you can infect any susceptible individual in the population, which is not very realistic, because we know that it depends on the connectivities. One of the simplest ways of modeling connectivity among individuals is to consider a model, a network model, such as an Erdős-Rényi random graph, or configuration model random graph, which is a generalization of Erdős-Rényi random graph, in the sense that in the limit of a large graph, Erdős-Rényi random graph assumes or dictates that the degree distribution will be Poisson, whereas configuration model random graph allows degrees to have arbitrary probability distributions. Long story short, if we consider an SIR model on a configuration model random graph, where the vertices are the different individuals that who could be in one of the three states, susceptible, infected, and removed. And if the infected individuals try and infect their susceptible neighbors, so the standard, let's say, mode of transmission, but only to their neighbors, restricted to their immediate neighborhoods, then in the limit of a large graph, we can show that this stochastic model converges to a deterministic system, which can be described in terms of the proportion of susceptibles, which are described by XS here, the proportion of infected, which are denoted by XI, the variable XI here, and XD, which is the density of infectious edges in the network. So XD is the amount of SI type of edges that are in the network divided by the susceptibles. Again, in this situation, you get these three equations to describe the dynamics in the limit of a large population, but upon fairly simple algebraic manipulations, you can show that this reduces to a single equation, which is written at the bottom. Again, the right-hand side is then the function h theta in my case. So if we observe a random sample of infection times, T1, T2, Tk, the likelihood contribution of these times will be simply negative derivative of the S curve, the susceptible curve, which is simply beta times XS times XD, which is the proportion of infectious edges. But they come from deterministic equations. So these are all known quantities. And my parameters of interest in this case are not only beta, gamma, and rho. So beta is the infection rate, gamma is the recovery rate, and rho is the initial proportion of infected individuals, but also mu, which is the average degree of the network, and kappa, which captures the density of, let's say, average network density. It's I will not give a precise definition of kappa here, but it's a quantity that measures how the average degree of each individual compared with the average degree of their neighbors, so size bias distributions. So when the degree distribution is Poisson, then the value of kappa is 1. If the degree distribution is a binomial, then the value of the kappa is less than 1. And if it's negative binomial, it's then greater than 1. So these are different parameter regimes for Poisson type distributions. But this is just another example. We can also look at an SEIR type of model. So here are the standard, let's say, ordinary differential equations to describe an SEIR model, where beta is your infection rate, 1 over gamma is the mean of the infectious period, and 1 over alpha is the mean of the latent period. If we have this system of 4 equations, but we can describe the same system by an SIR model with time varying rates. So which is described here. So if I denote by XS, let's say the proportion of susceptibles in my new SIR model, which I'm using to approximate it, the time varying rate is simply beta times the proportion of infected individuals in the original SIR model. So as a proportion of total number of infected individuals, both infectious and who are not. So individuals in the E compartment and the R compartment. And again, but as soon as we describe the system as an SIR type of equation, we know that this can be, again, reduced to a single equation, a pure death type equation. So we can write down a likelihood function, which will be simply this quantity. So these are all sorts of equations. Now, I'm just giving the example, but I haven't told you why this makes sense, or if at all, maybe it doesn't, so who knows. But anyway, if it didn't, then I would probably not be trying to tell you about this. So a rigorous justification of this likelihood function comes from the concept of propagation of chaos, which one can find in my joint work with Ganguly, which is already on arXiv, and hopefully it will come out in a journal soon. But today I will not go into the technical details of propagation of chaos, which is a classical topic in probability theory, but I'll try to give a simpler derivation using the Selke construction, which most people in the world of infectious disease epidemiology are familiar with. So that's my goal today. So let's try to see why this likelihood function makes sense. So in order to do that, I will start with an individual-based model. So let's say there are n susceptible individuals and m infected individuals at time 0. And this model, by the way, is the same model that you will find in the standard textbook of Anderson written, I think chapter 2 or 3, I suppose, where they describe the Selke construction. So for each individual I, I'm going to create some indicator functions. So SIT will be 1 if the individual is still susceptible at time t, or it will be 0 if it is not susceptible. Similarly defined II and RI. So the SI, II, and RI, these are just indicators of which immunological status the ith individual has at time point t. And I'll assume a simple Markovian setup, which means that if you get infected, then you have a Poisson clock, you have a rate beta at which you try and contact susceptible individuals and infect them. And if you are, there's another rate, which is gamma, at which you recover. Once you recover, there is no role for you to play in this system. So you're basically removed. So if we want to describe the trajectories of this system for these, let's say, indicator random variables at different time points, then we can use what is called the time change representation of Poisson processes, because so for each I, I'm going to use Yi and Zi as two independent unit rate Poisson processes. So if I start susceptible, then my Si0 will be 1. And then at some point, this Yi process will jump by 1, in which case the Si variable from 1, it will jump to 0, and then it will stay 0 forever. So it's a very simplistic process. Similarly, the I process, if it starts at I, at some point, the Z variable here, the Z process, will jump, in which case it will go to 0, and then it will stay at 0 forever. So all of these stochastic processes are extremely simple in the sense that they have only one jump in their entire lifetime. Now, so this is a more formal probabilistic description of their trajectories. There is an easy construction which we can use as an algorithm to simulate the system, which is given by Thomas Selke. So Selke construction works as follows. So to each individual, you assign a threshold, which is an exponential 1 random variable. And you keep track of the cumulative infection pressure, which is just this running sum of infectious periods. So so the sum here tells me how many infectious individuals are there in the whole system at a different time point. And each infected individual will be putting a pressure on each susceptible individual of amount beta over n. And I'm just integrating it from 0 to capital T. So even though this is an integral, we should keep in mind that this is a jump process. So the number of infected individuals, they are constant between two jumps. So this integral is essentially a finite sum. But the way it works is, now we have this infectious pressure, cumulative infectious pressure, which is building over time. And then as soon as it hits the threshold of an individual, the person gets infected. So this is, if I have to draw pictorially, so on x-axis, I have time. And on y-axis, I ordered these different thresholds. So these are all exponentially distributed random variables. And what I do is I just ordered them. So let's say I start with one single infected individual. So this green curve is the cumulative infection pressure. It will have a slope of beta over n, and it's going up, 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 up until here, where this crosses the first exponential distribution, and the first person gets infected. So Q1 does not necessarily mean that the person with index I gets infected. It is basically the person with the smallest threshold who gets infected. So now we have one more infected individual. So the slope of the curve will be now 2 times beta over n, and then it goes up and up and up. And at some point, somebody might recover. So then again, so which are these vertical gray lines here. And then we are again back to beta over n as the slope. But here we have the second infection where it reaches the second threshold, second smallest threshold, Q2. And then again, it goes up. And then there's another recovery. So the slope decreases. Here we get the third infection where it reaches the Q3, the third smallest threshold. And then there are 2 consecutive recoveries, which means that we don't have any more infected individuals left in the system. So then we end up with a flat line. And an implication of this is that anyone whose thresholds are larger than this flat line here, they can never be infected. So they will escape infection, which means that there's a positive probability that you will never get infected, which makes sense. Probabilistically, this means that if I want to calculate the probability that a susceptible individual remains susceptible till time point t, or remains uninfected till time point t, that probability, given the history of the process, is the same as the probability that an exponential random variable is bigger than the cumulative threshold up to time point t, right? But for exponential random variables, we know what is the probability that the random variable will be bigger than a given value. It is simply e to the power minus that value. The probability that an exponential random variable is bigger than 5 is simply e to the power minus 5 if the mean of the random variable is 1. So that's exactly what is done. But there's a reason why I'm showing you this formula, because we will see that the limit of this probability actually has a nice representation and coincides with something that we all know as a slightly different quantity. Okay, so now let's move from this micro model to the macro model, by which I mean that if I accumulate all these individual based quantities to a population level quantity, so number of susceptibles, number of infected, and number of removed, then again, this is still a Markovian system, and we can still describe their trajectories using these Poisson processes, which is just a continuous time Markov chain. And if we now let the population size go to infinity, then using the law of large numbers for Poisson processes, we can show that the scaled stochastic processes, the xn, which is just the proportion of susceptibles, proportion of infected, and proportion of recovered, they converge to the solution of an ordinary differential equation. So a system of ordinary differential equations, which is here in the left-hand side, we see, which coincide with the standard ODE system that we all know. If we solve this system partially, meaning that if I divide the first equation by st on both sides, then we see that, okay, st is nothing but e to the power minus beta integral of this. If we solve the other ones, it's very easy to get these sort of representation. But here's the interesting thing. ST is e to the power minus beta integral of IU du. But this is nothing but the limit of AN, the cumulative infection pressure, as n goes to infinity. And we have just seen that this quantity is nothing but the probability, the survival probability. So ST, the proportion of susceptibles in the mean field limit, is nothing but the survival probability up to time point t in the limit. So the conditioning on the history disappears, and this is just a survival function. This is just the probability that the random variable that represents time to infection is bigger than t, that a randomly chosen individual embedded in the mean field, a large population, hasn't been infected till time point t, that is simply ST. So, and if this is the survival function, then the density is simply the negative derivative of the survival function. We all know from basic probability, the density is the derivative of the cumulative distribution function, which is 1 minus the survival function. Hence, so the density is just negative derivative. So now it starts to make sense why we had this negative derivative term. So this is really the density of infection times. So this is basically what I'm trying to say is that from survival analysis perspective, the mean field model that I just have shown here on the left-hand side or also on the right-hand side, which is the limit of population-based quantities. These are proportions of individuals in different compartments. They are nothing but probabilistic quantities that describe the trajectories of individuals. So for instance, ST is nothing but the survival function. The curve I, if I solve this system of ordinary differential equations, this is how they look like. The S curve is simply a survival function. It's the probability that you haven't been infected. I curve is simply a density, and R curve is simply a cumulative hazard. It's very easy to see why they are so, because when we solve them here on the right-hand side, ST is, it's easy to see that this is the survival function because it is simply the limit of the survival probability in Selke construction. IT, if we discount for the first term, under this integral, this is just a convolution of the density of an exponential random variable, which is e to the power minus gamma t minus u, and S dot. But now we know that S is a survival function, so minus S dot is a density. So this is really a convolution of two independent random variables, which means this is again a density, and RT is simply the survival cumulative hazard, because RT is so ST is e to the power minus beta by gamma times RT. So this is really a scaled hazard function. So this is the dynamic survival analysis interpretation of these mean field models, and that's why these things kind of make sense. But so what we are essentially doing is that we are taking an ecological model, a population-based model, and then turning it into an agent-based model. So we can also do individual-based simulations, but we also get a likelihood function for free, which has a number of statistical benefits. So what are those? Well, the first benefit is that you get a simple product form likelihood function. Product form likelihood functions are very easy to work with. You take a logarithm and then you work with the log likelihood function, which reduces to a sum. Optimization becomes much easier. The other thing that's important here, you might have already noticed, that this likelihood function does not require any population level quantity. In particular, it does not require size of the susceptible compartment, which is typically problematic because in many cases, when you want to fit these models to a country or a city or a state, you typically assume the whole state is susceptible, which is not necessarily a good assumption, because we know from experience that not everybody in the state is susceptible, and there's the concept of effective population size, and this method can actually be used to estimate the effective population size as well. So not only does it not require any population level quantity, it can give you an estimate of the effective population size. And this will work even if the transfer times, by which I mean the infection times, And you can also write down the likelihood function for the recovery times or other times that you can think of. Even if they are censored or truncated or even aggregated, this will still work because of this survival analytic framework. Now, I mentioned before that the mass action models are often not very realistic. So let's look at a model on a graph. But before moving, is there any questions so far, or any comments or anything that I should clarify?
Not seeing anything in the chat or the Q&A, so I think you're good.
Okay. So let's move on to the next part, in which I will I'll tell you a little bit about models on networks. So there are many different kinds of networks, and I do not think that we have a good understanding of which networks are the best, because no matter how sophisticated or complicated network you build, we can always argue that, okay, this is not very realistic, and so on and so forth. And if you do end up making a very realistic model, then you cannot do anything analytically. So there's a fine balance between realism and analytic tractability that we need to strike. So I will choose a model for the network, which goes by the name configuration model random graph. This model is, let's say, slightly more realistic than Erdo-Shreni random graph, but it is nowhere as realistic as, let's say, stochastic block models or other types of models that allow for clustering in the network. So the model that I'm going to describe is still fairly simplistic. So how does it work? Well, there are two main modes of creating this model. One in which you specify the degrees for each of the vertices in the graph, and then you construct the graph. And the other one is, instead of specifying the degrees of the vertices, you specify a probability distribution for the degrees. For instance, a Poisson distribution, or a binomial distribution, or a negative binomial distribution, or some other distribution that you might have empirically estimated from data. But once you have given a probability distribution, and if I want to create a graph of size n, I will just draw n samples. Okay, there is a question in Q&A. How does your agent model look like? Can be easily simulated with Monte Carlo or state transition machine? Yes, the answer is is yes, because the model gives me the likelihood function for individual based trajectories. So once I have the survival function, you can, for instance, use inverse transformation. So you draw an uniform random variable, and then you fit it in the. So let me write down here how one could solve this. So for instance, we know that if I have a random variable x, whose survival function is f, so s of x is probability x bigger than x. And if f is its cumulative distribution function, which is probability s less than. So I'm assuming x is continuous, so these equalities do not make any difference. Now these functions, so we all know that f of capital X has the same distribution as s of capital X, and this is uniform 0, 1. So basically, one way to simulate infection times is to draw a uniform random variable and then doing an inverse transformation. So if you draw uniform and then if you do S inverse of U, then that will give you one sample from X. Now X, in my case, I'll just choose this random variable Ti. This is time to infection, whose survival function is St. So St is simply probability Ti greater than T. And St is, in my notation, is e to the power minus beta 0 to T u du, solves the ordinary differential equation. So if I want one sample from this, I will just solve one uniform distribution, or one sample from a uniform distribution, and then I'll just do the inverse. That will give me one sample from infection times. Now, once I get the infection time, if I just add an exponential with gamma, that will give me the same of a recovery time. Once I get infection time and recovery time sample, I've got a single trajectory. So this gives me a way of individual-based simulations. Okay, so let's go back to the graph construction. So yeah, so I was talking about configuration model graphs. So once we have decided the degrees for each vertices, so for instance here, I have decided the degrees to be 2 for the first vertex and sorry, 3 for the first, 2 for the first vertex, 2 for here. I will create half edges. So if I assign a degree of 3 to vertex 1, then I will just give 3 half edges to vertex 1. Once and so on. Once I have done that, I will pick 2 half edges uniformly at random and then pair them to create a full edge. So for instance, the 2 edges that just got disappeared, I will choose them and then pair them. So that gives me another edge here. Maybe this vertex and this vertex, they got paired, and then I get this. So this is a dynamic construction which allows me to create the graph one by one by pairing a pair of half edges. So this is a very simplistic construction. Of course, because of this simplistic construction, we can do certain calculations. It's analytically tractable. Now, how do we run the SIR model on this graph? Well, the dynamics is fairly similar to the dynamics in the mass action setup, which is a complete graph. So we have 3 different colors. And the blue colored vertices are the susceptible ones. Eye-colored vertices are the infected ones, and green ones are the removed ones. So if the middle vertex here is red, which means infected, so the infected vertices, they will try at a given rate beta, try to infect their neighbors at after exponential amounts of times. When they contact if the neighbor is already infected, then nothing happens. Or if already removed, then nothing happens. But if the neighbor is susceptible, then they get infected. So that's how it works. So this is a stochastic process. There are basic ingredients are a probability distribution, which so pk is just the probability that you will get a degree k, assuming mu is the mean of that distribution. So mean is the average connectivity, and beta is the infection rate, and let's say gamma is the recovery rate. And to mirror social distances, I'm also assuming that delta is the rate at which you are dropping your edges. So you can drop your edges to protect yourself, which is a feature that you may or may not want in your model. Now, this is a stochastic model, but as I described for the mass action setup, this stochastic process could be studied as the number of vertices in the graph goes to infinity, and as the number of vertices in the graph goes to infinity, using martingale techniques, we can show that the dynamics becomes more and more deterministic, and you will get a system of ordinary differential equations to describe the dynamics in terms of proportions of susceptible, infected, and removed vertices, but also in terms of different types of edges, because here the key drivers of the dynamics are the different types of edges. So edges that are connecting 2 infected individuals, or 1 susceptible and 1 infected individual. So once you get this system, again, you can do a fairly simple algebraic manipulation to show that it can be reduced to a single equation for S with these revised parameters. So beta tilde is just mu times beta. So the effective infection rate in this model is the infection rate times the average degree. The effective recovery rate in this model is beta plus gamma plus delta, and rho is tilde is just this. But the bottom line is, once we get this one single equation, we know how to write a likelihood function. So we can just do our analysis, and we can fit this model. So actually, this is precisely the likelihood function we used when we were supporting the governor of Ohio, and the pictures that they were showing in the press conferences there, they were actually generated using this. And I was the one who was doing it back then, so it made me very happy to see that. Okay, my pictures are yeah, are being used somewhere. So it was a very good experience for me. Anyway, one side note that I want to mention here, which is a curious observation that came out of this this analysis, is that if I have already shown you that if I have a mass action SIR model, you can reduce it to a single equation that looks like the equation that I have described here in red. And I have just shown you that if I have an SIR model on a configuration model random graph, which is much more complicated as an object than the mass action model, then again, I've shown you that this could be reduced to a single equation that looks like the one that's in green here. If I compare these two equations, you will see that they're basically the same. So of course we have this beta tilde and gamma tilde and rho tilde here, which is beta tilde times rho. So their interpretations are slightly different. So beta tilde, as I mentioned, is not the infection rate, but the effective infection rate. It's the infection rate beta times the average degree, and so on and so forth. But we get the same set of equations. So as far as dynamic survival masses perspective is concerned, the model on the network is actually equivalent to a mass action model, but with some reparameterization. So we can think of a network model in this case with Poisson degree distribution is a reparameterization of a mass action model. And this also explains why the SIR model often fits data fairly well, even though we know that the true underlying model cannot be a mass action SIR model. So we wanted to understand, of course, if there are multiple peaks and so, then you cannot fit a single SIR model, that's for sure. But it is often the case that SIR model, even though it's very simple, does a fairly good job of fitting it. So we wanted to understand, okay, so what other types of model can the SIR model approximate? And I've already given you an example, it's the standard SIR model, SEIR model. So even though there is an additional compartment, we will see that it can be also well approximated by an SIR model to the point that we can even fit an SIR model to estimate all the parameters when the data comes from an SEIR model. So I will generate, I know the ground truth. The ground truth is an SEIR model. I'll generate data from it, but I will show how we can still fit an SIR model with arbitrary accuracy. Okay, so that's my goal in the last 5 minutes or so. Okay, I'll start with the standard stochastic SEIR model, which is, I'll not go into the detail, but the same recipe, we look at the counts of S, E, and I and R at different time points. We can describe their trajectories. We'll assume that it's a continuous time Markov chain model, so we can describe its trajectories by via the random time change representation of Poisson processes. We get these equations, and then if I scale the system by n, which is the population size, the proportions, they converge in the limit to solutions of ordinary differential equations, which look like the standard SEIR ordinary differential equations. And if I want to now approximate the SEIR model by an SIR model, what I'm going to do is I'm going to take the solutions of these SEIR ordinary differential equations and note that the main driver of the epidemic is the individuals in the I compartment. So of all the individuals who are infected, which I'm going to denote by VT, which is the sum of individuals in the E compartment plus the individuals in the I compartment, of this pool of infected individuals, the main driver is IT over VT, the proportion of individuals in the I compartment of all the people who are infected. Now I'm going to build a time-varying SIR model where I'm going to say that instead of beta being the infection rate, I will vary the infection rate as a proportion of beta times IT over VT. So I'll multiply beta by IT over VT. So that will adjust for the relative amount of infectious individuals at different time point t. And in order to account for the recovery rate, I will also multiply gamma, the fixed recovery rate, by gamma, multiplying gamma by IT over VT, gamma times IT over VT. So this gives me two time varying parameters. And then I'm going to assume I have standard mass action SIR model, but with time varying rates. So now you might say, okay, but this looks funny. Is this a good approximation? And it is actually. So in the limit, you can prove that both these systems, they will converge to the same thing. So this the fake SIR model that I just created will also converge to a system of ordinary differential equations that look exactly like the standard SIR equations, except that the infection rates and the recovery rates are now time varying. But if I look at the S component here in this system and the S component of the original system, they're actually exactly the same. So we can prove that they will be exactly the same, which has the added advantage that we can now use this for my inference. So if I just draw infection times from the SIR model, and if I draw infection times from the SEIR model, their densities, the empirical densities, look very much the same. So the bottom line is, of course, as we can approximate an SEIR model with a time varying SIR model when the population size is large. Of course, when the population size is not very large, so for n equals 10,000, we see that these densities are almost the same. But when n is equal to just 1,000, if we are thinking of a model with just 1,000 individuals, then we are far from the true law of large numbers regime, and there is a bit of error. But we can actually quantify the error. So I'll provide a concentration inequality to quantify the error. So let's look at this variable delta, which will quantify the component-wise error in the two models. So I'm taking a difference between S, E, I, and R from the original stochastic model, and I have the S tilde, V tilde, and R tilde from the fake SIR model, or the approximating SIR model. Now the V in the new SIR model, that accounts for both infectious and non-infectious infected individuals. So if I multiply my V tilde by IT over VT, that will give me the true infected infectious individuals, and 1 minus that will be this. So if I look at these component-wise differences, then you can prove that over a compact time interval, the probability that this difference will be large, let's say epsilon, bigger than epsilon, is actually very small. It's exponentially small, so it's smaller than e to the power minus square root of n. So it decays rapidly. There's this additional term here, which has an indicator of the fractional part, but we can safely ignore it because fractional part is less than 1. So 1 over n, that goes to 0. So this part, the first part here, that just disappears very, very quickly. So the essential rate is the second part, and it shows that it decays exponentially fast. So the error that we are making in the fake SIR model is actually not that much. We tried to fit this fake SIR model to data generated from an SEIR model, and that was quite fun. So how do we do it? Well, again, we have the DSA perspective. So if we just look at the ST curve, we know that we can interpret it as a survival function for the time to infection random variable. So given a sample of infection times, we can get this as the likelihood function, just the product of these negative derivatives. I'm missing a negative here, -1 here in FT tilde, because it has to be negative derivative of the survival function. And if we assume that we have some recovery times, then again, I told you before that we can just do a convolution, and that will give me a density for the recovery times as well. But it's not necessary. We can do inference based only on infection times. So here I'm showing some simulation studies where we took a very small sample of infection times out of a large population, and these are the posterior plots of, let's say, posterior draws of these different parameters. So alpha, the latent period, in infection rate, beta, infectious period, gamma, and the proportion of infected initially, rho, 4 parameters. You see that they are estimated fairly accurately based only on infection times and nothing else. If we add recovery times as well for some individuals, they don't have to be the recovery times of the same individuals for which we have infection times. They could be completely different, and in the limit, everything becomes independent. So they just have independent contribution in the likelihood function. We see that if we can supplement with the recovery times, then we get much better. The quality of inference becomes much better, and we get better estimates. So with that, I will stop here. So I'll just summarize what I've told you. So I started with an, I think, ad hoc likelihood function for a pure depth type of system, but this pure depth type of system is just an abstraction for a lot of different types of compartmental epidemic models. For instance, SIR, ACIR, those type of models. Even on networks, they can be seen as just a pure depth type of perspective system from the perspective of a susceptible individual. So that's why. So this ad hoc and likelihood function is actually not so ad hoc because of the Selke construction for epidemic models. When the system is not an epidemic model, we in the paper or the archive, it's an example from systems biology. Then we can still give a rigorous justification using propagation of chaos. A benefit of this method is that it does not require size of the population, susceptible population, and the other benefit is that your data does not have to be exact. It could be any transfer times, so infection times or recovery times or hospitalization times or death times for any individuals. It does not have to be the same individual, and it does not have to be for all individuals. In fact, it should not be for all the individuals, because in which case we will break independence and they could even be censored and truncated. So with that, I'll stop here and be happy to take your questions.
Great, thank you. Very interesting talk. I would be severely overstating it if I said I understood all of the implications of what you just presented, but it sounds really fascinating. Folks have any questions, please feel free to put something either in the chat or in the Q&A, and we'll take them. But let me just throw something out here that occurred to me as you're going through this, that you sort of present an argument, if I understand you right, that the SEIR and the SIR models are really functionally equivalent, just with some difference in the parameters. Am I understanding that right? And does that suggest maybe then that all of the folks who have been trying all of these different extensions to SEIR, that we may not really, in a theoretical sense, be gaining much from that?
So it is yes and no.
Okay.
So yes, from the perspective of susceptibles. So if we are willing to ignore, let's say, other pieces of information that are very important, then yes. So if we are only interested, so I think Otto Diekman was that like we should be modeling the force of infection and just the rate at which susceptible individuals are getting infected. That carries a lot of information about the disease. So if we look at only the rate at which susceptible individuals are getting infected, the force of infection, or from the perspective of susceptibles, then yes, these are the same models. These are equivalent. So you can reparameterize one to get the other. But if I look at not just infected individuals, susceptible individuals, but also in different compartments, you will start to see some differences, because the rate, so the transfer of susceptible individuals out of that pool is the same in both models, but their behavior in the other models could be different, which makes sense. And this is also the point when I tried to make about the equivalence of a network model and a mass action model. The transfer of susceptible individuals out of the susceptible pool, if I just only look at that, then a mass action SIR model and a network model with Poisson degree distribution, they're exactly the same. There's absolutely no difference. You can get one from the other by just reparameterizing. But if I want to look at other quantities, like people with prevalence, and they could be different because the model itself might have very different behavior. But from the perspective of inference, we would often, as statisticians, we like to build methods that would require the minimal information, or minimal. We don't want to make methods that are data hungry, rather they can work with. So the whole idea behind developing this thing, while at the start of the COVID pandemic, was that we didn't have a lot of data. We had very little data to make sense of what's going to happen, and the governor was asking lots of questions that could not be answered otherwise. So that's the both yes and the no. So yes, from the perspective of the susceptibles, but if you want to look at other quantities, then no, they are different models. Yeah.
Great, thank you. We have a couple of questions here, which I'm going to sort of summarize. Really to start with here, just saying, how much data do you need to get to start getting some good guesses on the parameters? And so the one comment follow-up there is, would a month of data be reasonable? How much do you think you need?
In general, so the more the better, right? So at the start of the pandemic, I think back in March 2020, when we were asked to produce some results for the governor, we didn't have a month's data, but also we had a huge uncertainty in our predictions and in our estimates. But as we collected more and more data, then we could reduce uncertainty by a fair amount, and so on. So how much is enough? That's a difficult question, because it will really depend on. So we can answer that from, let's say, synthetic data, but synthetic data is too good, because you already know what the ground truth are, and you already know that the true generating process is what you started with. But with the real data, we were getting, let's say, decent estimates after a month or so. It's but it's not always going to be like that. Now, there's another point of how much data is enough, but how much data is too much. So because this works with propagation of chaos, this method is only good when you have a small amount of data rather than a lot of data. So if I do, let's say, a simulation using cell key construction on 1,000 individuals, and if I take each individual level data of all 1,000 individuals, then this likelihood function is absolutely rubbish, because we know that these individuals are not independent. So even if I claim that we just take this product from likelihood function, that's not going to be true. So there is a limitation. So as long as our observed data is at most, let's say, square root of n order of the whole population, then the independence still works through, and we will get good consistent estimators. So that's that's the, let's say, that would be my answer. So I think whether 1 month's data is enough for a real epidemic, I mean, in my experience, they seemed to be enough, but of course, I think in general, I don't think we can give an answer.
Great, thank you. Okay, then this other question here about can you detach from the regular PDE format of SIR variants and estimate something like an infectiousness generation curve and not just infection and recovery events?
That's a great question. So actually, I mean, I didn't present it today, but we were able to develop this methodology for even a non-Markovian SIR model. So we have a paper about that in Interface, where we look at non-Markovian SIR model, where your infectious period and the recovery periods are arbitrary distributions described by your chosen hazard functions or survival functions, however you want to describe them. And it could be Weibull, log normal, or any distribution even you want. And in the limit, then you get PDEs instead of ODEs, partial differential equations. But the same cell key construction type of idea still works there, because from the perspective of susceptibles, you can think of, okay, so when am I going to get infected? Well, you will get infected when your threshold is crossed by the cumulative infection pressure. Even though this cumulative infection pressure is now adding infectious period that are not exponentially distributed, but still the idea is still the same. As long as the cumulative infection pressure crosses your threshold, you will get infected. So we can still write down a likelihood function, and we can still estimate the parameters of these general distributions. We tried Weibull, I think Weibull gamma, inverse gamma, and yeah, several other distributions, and we were able to estimate them from synthetic data, but we were also able to fit those models to COVID-19 data from India and some other countries. But in India particularly, we observed that the non-Markov model gave a much more reasonable fit than a Markovian SIR model, or correspondingly an ODE model, in terms of the peak and in terms of also predictions. So yeah, I mean, in general, I think, as Van Kampen once put, that non-Markov is the rule, not the exception. So so it's a great question. Yeah, we can do that.
Great, thank you. I think we're about a few minutes past the top of the hour, so I want to thank you for taking time. We do have a question. Somebody who wants to get in touch with you. If you could stick your email in the chat, that would be great. And otherwise, I'll say thanks to everybody for attending. Thanks for a nice talk, and we will look forward to hearing you at the next seeing you at the next webinar in July. Thank you so much, everyone.